Right, so welcome back, and we are continuing our study of functions, inverse functions and logs, and this will probably be our second last lesson on this. So without any further ado, let's dive straight in. We're on page 92, and we're looking at the bottom of page 92, and we're asked to find the equations of the axes of symmetry. Now let's just remind ourselves about axes of symmetry for a hyperbola. Okay. So let's see if I can improve on that line there because it wasn't great. Okay, that's a bit better. And now just remember that all hyperbolas, irrespective of which quadrants they're in, this one's actually in these two quadrants, right? But all hyperbolas, before they get moved, have these two axes of symmetry, right? This one over here, which has got a downhill gradient, a negative gradient, y equals minus x. And this one over here, going uphill, y equals x. And the important thing is that they have gradients of 1 and minus 1. And the other important thing is that they always pass through the point at which the asymptotes intersect. All right, so we're going to do this question in two different ways, just because we think it's helpful for you to see both things. All right, so the x asymptote of this is x equals minus 3, and the y asymptote y equals minus 4. So what we want is we want lines with a gradient of 1 and minus 1. Plus or minus 1 as gradient. But we also want them to pass through the point negative 3, negative 4. Okay, so let's just take a look at how that's going to look. All right, we quite like to use this formula. Y minus the y value is the gradient x minus the x value. All right, and obviously the other one would be with a gradient of 1. So just to short circuit this a little bit, we're going to get y plus 4. And here we're going to get negative x. This is going to be subtract 3, negative x minus 3. And so we're going to get y equals negative x minus 7. That's the 1. If we had a positive 1 in here, then we would get y equals, here we'd get positive x, we get positive 3, here we've got a positive 4, subtract 1, we would get x, take away 1. Okay, so those are our two axes of symmetry. A gradient of 1 and a gradient of minus 1, both of them passing through this point. Okay, now let's take a look at another way of thinking about this. If we just think about these axes of symmetry, y equals x, all right, that axis of symmetry, when the graph moves 3 to the left and 4 down, the axis of symmetry must as well. And remember, the way that we move a graph 3 to the left is we add 3, and 4 down we subtract 4. And this equation over here is exactly that equation over there. The other one, think of y equals minus x. But now what we need to do, we need to, instead of an x here, we're going to move it 3 to the left and then 4 down. Right, and this one, if we simplify it, comes to minus x minus 7. And so there they are. Okay, so two kind of different methods, both of them equally good. Right, let's look at question 34. What question 34 says, for what values of k will this parabola and the line y equals 2x plus k not intersect one another? Now we will draw a little picture of this just now, an animated thing to confirm our answer. But let's just have a look at what we've got here. We've got a parabola. We don't know exactly where it is. We do know that it's a kind of happy parabola that way up. And then we've got a line y equals 2x plus k. And what the plus k is going to do is going to move that line up and down. As I've drawn it at the moment, they do not intersect. But obviously, if k was bigger, then they would intersect. There'd be a point at which they'd just touch, and then there'd be a point after which they would actually intersect. Now, when we want to find out where graphs intersect, what we do is we solve them simultaneously. So we're going to put the two right-hand sides equal to one another. X squared plus 3x minus 3 equals 2x plus k. Now what we're going to do is we're going to form a quadratic equation on this side. So we get x squared plus x minus 3 minus k. And we want that to have no solutions. Now remember, a quadratic equation has no solutions when the discriminant, delta, is less than 0. Okay? So delta is going to be 1 squared minus 4 lots of 1 lots of minus 3 minus k. Minus 3 minus k is our c value. And we want that to be negative. Okay. Now the only variable left in here is k, and we should be able to solve for it. What we get here is we get 1. We're going to get minus 4 times minus 3, that's plus 12. We're going to get minus 4 times minus k, that's plus 4k. We're going to subtract 13 from both sides. So we want 4k to be less than negative 13. So in fact, k must be less than negative 13 over 4. Right, what we're going to do now is we're actually going to have a look at a sketch of this just to confirm that answer. Okay, so here we've got a picture of each of those two graphs. We've got x squared plus 3x minus 3, and at the moment we've got y equals 2x, right? And we can adjust the value of k, right? And then we can see that if we pick the line up, obviously it continues to hit that graph twice. The blue graph hits the red graph twice. But if we drop it down, if we make it negative, the blue graph's now dropping down. Now we got negative 13 over 4. Now negative 13 over 4 is negative 3 1/4. At negative 3 1/4, the graphs just touch one another, right? We actually say that the blue graph is a tangent. But as soon as k becomes less than negative 3 1/4, the graphs miss one another. Okay. Right, these questions are around interpreting functions, and a lot of people find these quite challenging, but let's just look at what's happening. At the moment, there's the function f of x. It has got 3 x-intercepts. Okay, now the question says, what values of t will cause it to have exactly one x-intercept or one root? Now, in order for it to have one root, we would need to pick it up. If we picked this graph up, it would go up somewhere like that. And how much would we need to pick it up so that this point is actually on the x-axis? In fact, we want it to be a little bit higher because then it will only have one x-intercept. It will have this one on the left here, all right? Only, all right? So let's take a look at that. Okay, we would need, in fact, we would need to pick it up by exactly 20,7. And to pick it up by 20,7, t must be positive 20,7. Alternatively, we want to pick it up by more than 20,7. So t must be bigger than 20,7. Or we could drop it down, because if we dropped it down far enough, for example, down to here, then it would only have one x-intercept as well. Right, so let's look at how much would we need to drop it down. Well, we would need to drop it down by more than the y-coordinate of that turning point. So t would need to be less than, now remember we're dropping it down, we want it to be negative, so less than negative 12,6. A number like negative 13 would do, because it would drop it down by 13. Okay, right, the next one, look where this plus k is now. This is actually going to move the graph left or right. Okay. Now it says, for what values of k will that equation equal to 0 have only positive roots? At the moment, it's got 2 negative roots and 1 positive root. Which way would we need to move it for it to have positive roots only? That's right. We would need to move it to the right. and we would need to move it far enough right that this point becomes positive. We would need to move it more than 4 to the right. But remember, to move it to the right, we actually want negative values. So in fact, we need k to be less than negative 4. Think of negative 4, 1. That would move the graph 4, 1 units to the right, and all the roots would be positive. Okay, then this is an up-down one again in C. All right, this is up-down. We know it's up-down because the plus t is being added at the back. All right, for what values of t will f of x plus t equals 0 have 3 distinct roots? At the moment, there are 3 distinct roots. All right, we can pick the graph up or down. We can drop it down, okay, by 12,6, not quite as much as 12,6. So we would need to drop it down by a bit less than 12,6, all right, or we could pick it up by a little bit less than 20,7. And remember, the picking up is a positive value, so that's 20,7. So we want t to be less than 20,7, but we also want t to be bigger than negative 12,6. So let's just think about numbers that are inside there, like negative 11, all right? Negative 11 would drop it down by 11, and the graph would just be like that. And we would still get 3 distinct roots, okay? And 20,7, if we picked it up by 20,7, not quite 20,7, less than 20,7, like 20,6, the graph would be like that. Okay, people don't find these questions easy, but we hope that this is helping a little bit. Okay, then it says, for what values will we get 3 roots of the same sign? Now, there's 2 possibilities here, and we've already looked at making all the roots positive. If k is less than negative 4, we will get all the roots positive. But what's the other possibility? We could move the graph to the left so that all the roots are negative. How much would we need to move it to the left so that all the roots are negative? We need to move it more than 3. And remember, when we move it to the left by 3, we are adding 3. So k bigger than 3. And there's our answer for that. Okay, we will quickly show you just a little simulation of this maybe a little bit later. Okay, right, let's move on now to finding equations of some functions. And really the crucial thing here is working out, what are we dealing with? Well, this one is a straight line, right? Pause the video, try these questions if you haven't tried them yourself yet, and then let it play and see how you did. Okay, so this first one, straight line, let's work out the gradient, right? It's dropped down by 4 in the time that it's run across by 6. The gradient is negative 4 over 6. We can do that in other ways as well. We can do it using a formula. If we take the y value of that point minus the y value of that point, just remember that we mustn't swap around. If we went from this point to this point, now negative 3 minus 3. And what we get is we get here 4 over negative 6, which is exactly the same as negative 4 over 6. Both of them are negative 2/3. Now we've got a choice. We can either use y equals mx plus c, and we suspect that's the one maybe that you're more comfortable with, so let's use that one. So we've got y equals mx plus c. We're going to go 7. In fact, you know what, I'm going to use this point, and the reason I'm going to use this point is because we just want to make the point that 7's a y value. Here the x and the y value are the same. 7 is negative 2/3, that's our gradient, times our x value of negative 3 plus c. Okay, so just to sort of color code a few things here. This number over here is our gradient. There's our gradient. Same number, simplified on the second line. This here is the y value. Y equals gradient times x, and this here is the x value. Okay, right, there's only one variable left there, and that is our value for c. So what we're going to do now is we're going to multiply this. We're going to get 6 over 3. This is 21 over 3. 21 over 3, subtract 6 over 3 from both sides. All right. So this is 6 over 3, which is actually 2. All right. So we're actually going to get 5. We get c equals 5. And so we get our final answer, y equals negative 2/3 x plus 5. And that looks about right, because that graph's got a y-intercept of 5, and that looks about right that that would be 5. Okay, the next one, what are we dealing with? What sort of graph is this? Absolutely, it's a parabola. Now the vanilla form, or the parent function for parabola, is ax squared. Okay, but ax squared actually would turn there, right? This one's moved. How do we know how much it's moved? Well, it's moved 4 to the left and 3 up. 4 left, 3 up. So we need to take this graph and we need to move it 4 to the left and 3 up. How do we move a graph 4 to the left? We add 4 to every x value. How do we move a graph 3 up? We add 3 at the back. Every single parabola that turns at negative 4, 3 has this form. Okay, now we want the specific one that also passes through the point negative 2, negative 5. What we're going to do now is we're going to substitute that point in to our equation. We're going to pop it into there. Remembering that the y value is negative 5, the x value is negative 2, and the only variable now in there is a. Right, sorry, that's a plus sign, rather tatty looking plus sign, and that's a 3 on the end there, my apologies. All right, so now this is going to become, we're going to subtract 3 from both sides, we get negative 8. Inside the brackets we get 2 squared, which is 4, so we get 4a is negative 8. We get a is negative 2. Did we expect a to be negative? Impella, of course, because this graph is facing downwards. It's a sad faced parabola. Okay, we're going to, when we do some calculus, we're going to learn a better name for it, but for now we'll just call it a sad parabola. Okay, now let's write it in standard form. So what we're going to do is we're going to multiply this out. So it's negative 2 into x plus 4 all squared plus 3. X squared, so negative 2x squared. 4x doubled is 8x, but multiplied by negative 2, negative 16x. And then we've got 16 times by negative 2, that's negative 32, plus 3, negative 29. Negative 29, okay, and we've just managed to squash that in on the edge there. Okay. Right, the next one, if you haven't tried it, pause the video and try it. But let's, in fact, you know what, let's stop there. Before the next lesson, try these remaining 6 questions. So these 2 and then the 4 on page 95. We'll see you next time and we'll go over them then.